Hello everybody. In today's lecture we're going to be discussing a little bit about ground improvement, particularly ground improvement to remediate risk or hazard that might be there due to soil liquefaction. We've talked a little bit about liquefaction in previous lectures, and specifically how to consider three important aspects of it: susceptibility, initiation, and its effects. Now, if we do an analysis and we determine that our site is susceptible to liquefaction, it's predicted that liquefaction will initiate, and the anticipated or calculated effects from liquefaction are not acceptable to the performance of our infrastructure on our site, then we have to do something about it. We have to remediate it. Now, there's different things we can do. One thing we can do is just increase the stiffness or the strength of our structure to resist the loads and deformations that we anticipate will be applied due to the liquefied soil. That's one thing that we can do. Stiffness of structure. The other thing, though, that we can do, and that is commonly done, is just improve the quality of the soil itself. And try to remove or take away its ability to initiate or change its susceptibility to liquefaction. If we take one of those two things away, or both, then we can avoid the negative effects associated with liquefaction. And so we refer to this improvement of the soil typically as, of course, ground improvement. So with ground improvement, what we're trying to do is physically or chemically alter the soil conditions at the site so as to make them more favorable for whatever objective that we're trying to achieve with the site. We don't just do ground improvement for liquefaction. We do it for other things as well. If you have unstable soil due to landslides or slope issues, if you have organic soils that could have excessive settlement, and the list goes on and on. Anytime you have undesirable soil conditions and there's no way to stiffen the foundation or to design the structure to withstand the effects you're anticipating, often we rely upon ground improvement. So for instance, in this figure down here that you see, we have a machine that's installing reinforcement elements into the ground along an anticipated failure plane or shear plane that we're worried about that might have a slope stability problem. So ground improvement today is typically designed and installed by geotechnical specialty contractors, and there's a whole bunch of them out there. I've just thrown a couple that I've worked with and I'm familiar with here on this slide. This isn't intended to be a commercial for them, but these two generally fall under the same parent company. Nicholson is under the Menard parent company. Hayward Baker, really big here in the United States. And then Malcolm Drilling, they're also really big. They're newer, more of a startup, I'd say in the last 10 years or so, but they've done a lot of big projects and good work. So a couple of things that you need to understand about ground improvement. Some students may and have asked me the question, well, why don't we just do ground improvement for every site? Well, here's the problem. It's because it's really, really expensive. Ground improvement in general, based on my personal experience in consulting, generally increases the total cost of the project by 3 to 10%. I'm not talking the cost for like the geotechnical exploration. I'm saying the total project cost increases it between 3 to 10%. So if you weren't anticipating that, you can imagine that this could be a very significant increase in the budget. So if you're going to spend that kind of money for this service, you want to make sure that you're doing it right the first time. You want to make sure that it's effective and that you don't have to go back and redo something that somebody did wrong a previous time. So there are lots of different types of ground improvement, and all of them have different various applications. And the funny thing about ground improvement is these contractors are extremely creative, and they're constantly tweaking, adjusting, changing, inventing, and coming up with all new ways and methods to improve the soil. And so the stuff that I'm going to show you today is think of it as generalities. They're some of the tried and true, more common techniques. But if you go to any individual geotechnical contractor, they may have their own patented approaches or things that they do that's unique to them. And so what the list that we're going to talk about in this lecture is by no means a complete or exhaustive list of all of the ground improvement options that are out there. If we take ground improvement and just lump it into general categories, we can come up with essentially 6 modes or categories by which ground improvement improves the soil. I think the first one is soil densification, soil drainage, increased reinforcement, compensation. This is an interesting one that we'll talk about. Replacement of the soil, and confinement of the soil. So go ahead and take these notes down, pause if you need to, but what we're going to do is talk about some of these different techniques, and then I'm going to show you which one of these 6 categories the technique fits into. And I really like this tabulated summary from a good friend of mine, Dr. Brady Cox, who's currently at the University of Texas. When he made this table, he was at the University of Arkansas. But it's a summary of different methods of improvement, and it summarizes the different mechanism by which that method improves the ground. So we're going to try to go through and talk about each one of these methods in this lecture and introduce you to them. So the first one is vibratory compaction, and sometimes we call these sand piles. So with this, we have a crane set up that lowers basically it's called a vibro-float, a vibro-flotation device. It's just a giant vibrator that we lower down in the ground, and it vibrates and densifies and compacts the sand in the vicinity of the vibration device. And so then what happens is somebody at the top shovels sand down the hole that's created, and they just keep shoveling sand. And the point is that we're adding more volume to the loil and increasing its relative density. So we're compacting the soil down here. And this vibro flotation device is lowered down and up, and it just goes up and down, compacting the soil. And then once it's done, they scoot it over and they do another one. So the nice thing about this, you can install it wet or dry. It can be effective in siltier soils if you have improved drainage. And so you may need to install like PVDs or wick drains to improve the ability of the soil to compact. It is not effective in clayey soils, not at all. So one of the things to be aware of, though, is when we do this method, it requires improvement of the entire soil column, not just a specific depth. So say that you have a zone down here of liquefied soil that you're interested in, but say you have a dense zone up top. Well, in order to get to this stuff down here, the loose stuff, you've got to improve and go through the dense soil as well. And so you're going to improve the entire soil column, not just a targeted region or zone. So the way that this method works is we're going to improve the ground by densifying the soil, increasing the relative density. And it's also going to improve the drainage of the soil because we're adding clean sand to the soil, which increases its ability to drain water out. Okay, the second method is a popular method. It's used quite commonly. It's called stone columns. Stone columns works by densifying the ground, improving the drainage so that the soil is less likely to liquefy, and it also provides increased shear strength to the soil, which by definition is a reinforcement. So the way stone columns work, we have the same vibro-flotation device that we lower up and down in the soil. But this time we have a hopper, or it looks like a big garbage bin, loaded up the top of the crane, and there's a tube, a big pipe that runs down, right down by the bottom of the vibro-float. And what we do is we load a bunch of very jagged, it could be medium grained or medium sized gravel into this hopper. And as our Vibrofloat goes up and down, the gravel comes down through the chute and exits down into the void space that's created by the Vibrofloat. And so what we end up with is a column of compacted, angular, sharp gravel up and down, and we can then do these columns kind of on a grid or a pattern beneath our structure or site. So again, stone columns can be useful in silty soils if we increase the drainage by using PVDs or wick drains. Not effective at all in clayey soils. Another thing to remember about this is, just like before with the sand, we're going to have to improve the entire soil column. We can't just focus on a specific depth or a specific layer of interest down here. We have to improve all the way from the layer of interest up to the ground surface. You might be interested to know that this technique is what they use beneath the Life Science building on the south side of BYU campus. Another method is called Vibro-Concrete Columns. So same idea as stone columns, but instead of gravel in the void space that's made by the Vibrofloat down here, we're just going to pump concrete or grout down, and that grout is what's going to fill the void space in the ground. So this improves the ground through densification and reinforcement. Putting grout in the ground does not improve the drainage of the soil. So one of the nice things about this is that we can install these in fine-grained soils. Oftentimes we can't use the vibro technique. We have to drill it first because the clay just doesn't compact with vibration. But the point is that we can get down and we can put this grout or concrete in the ground. But if we do it in fine-grained soils, we're not densifying anything. We're just reinforcing the soil by applying an element or a material that has an increased shear strength. Also, because these columns now are comprised of grout or concrete, which is a material that is very strong in compaction, these columns can somewhat act like piles, transferring a lot of the load from our structure up here above down to soil layers that are deeper down. Now that can be a good thing and it can be a bad thing. It depends on what your soils are like down in the deeper layers, and it also depends on what and then make sure that you design the concrete columns to be able to work like that. Like before, this method requires improvement of the entire soil column, not just a specific targeted depth. Deep dynamic compaction. This is a really interesting and really fun to watch technique, and the idea is you get a crane out to the site, and the crane is really tall. It can be I don't know, probably 100 feet plus in height. And then it's got a big weight. This is usually like a 25 to 35 ton weight that it picks up to a height of, anywhere between 100 to 80 to 100 feet. And then they're just going to drop it and let it free fall and come and bang into the ground. When you bang a weight that's that heavy into the ground, it's going to send waves down into the ground, and those waves are going to compact the soil down to depths of, they can compact to depths of up to about 10 meters maximum. but they're only effective in compacting cohesionless, not cohesive, but cohesionless soils. So this really is going to work by densifying the soil. That's the only thing that we're doing. We're not adding any new soil to it. We're just densifying it from the ground up. This method is not effective in fine-grained soils, clays or silts, or soils that have a fine-grained superficial layer. So if I have like a layer up here that is clay and then sand down below, that energy is just going to get all gummed up in the clay and won't make it down into the sand. So we want to avoid any time where we have a fine-grained layer near the ground surface. And the other thing to be careful of, as you can imagine, this method produces a whole lot of noise and vibration. And because of that, it's very disturbing. So if you have a lot of neighbors or buildings around, especially buildings that might be sensitive, this is not the method for you, because it will induce vibrations and it will induce a whole bunch of noise that can be disturbing to the community and the neighbors. So I can't show you this video again because I'm posting it on YouTube, and I don't want to get in trouble by YouTube by showing copyrighted stuff in this video that I'm recording. But I'll put the link down to the video in the description box. It's a fun little video that shows a fun application of deep dynamic compaction. Okay, here's a different method. It's called compaction grouting. It's a method that, well, I've used a few times on various projects. What we do with compaction grouting is we have a specialized rig that has this tube on it that can lower itself and basically push itself down into the soil to whatever depth you're interested in. And then what it does is it pumps grout down through the bottom of this bulb, and it can pump it under pressure so that it produces just a big gloppy bulb of grout. And that gloppy bulb just pushes all the surrounding ground out of the way, and so in essence, in doing that, it densifies the soil, but it also provides some reinforcement to the soil as well, because now we have this big gloppy column of little grout bulbs. So, you know, if we have cohesionless soils, then it certainly will densify the soil. If it's not cohesionless and it's cohesive, it just provides some reinforcement to the soil. One of the biggest advantages of compaction grouting is that we can target specific depths. We do not need to improve the entire soil column. In addition to that, we can get this thing into some pretty tight places, like they show this column that's beneath this building. You can get these devices into the basements of existing buildings and improve the ground beneath existing buildings, or you can go in at an angle and do bulbs on an angle, you know, beneath footings or those kinds of things. But you have to be careful, because when you pressure grout this stuff into the ground, it can jack the ground and it can jack footings easily. And so, you know, you want to make sure that you have a professional who knows what they're doing and can monitor this stuff. One of the problems is, because we're getting grout in the ground under enormous pressures, is that it can be difficult if we're in shallow soil, so in depths less than about 20 feet. That's because the pressure will just work its way right up to the surface, and then you get these big blowouts on the ground of grout, and it's not very fun. And then finally, it can be difficult. You know, right now this diagram shows these nice, pretty, even, uniform little bulbs of grout. In reality, it probably doesn't look at all like that. It's messy, it's probably not uniform, and so quality assurance, being confident of the quality of what you have can be difficult. Okay, the next form of ground improvement is called permeation or chemical grouting. Permeation or chemical grouting is basically we set up a series of pumps or basically we permeate a treatment or grout through the soil until that grout saturates the pore space in the soil. So it has to be a pretty soupy and runny grout. And so it's going to make kind of like a soilcrete. And then once the soilcrete hardens, we can do lots of stuff. Like we can improve our lagging for an excavation, or we can support a footing at the base of an excavation that could prevent seepage going into our hole. We can use it to prevent water at the base of an excavation in water. We can use it to prevent seepage or strengthen the lining of a tunnel. I mean, there's all sorts of things we can do. I mean, once you have this grout, this big tunnel of grout, it's easy for a tunneling machine to come and just bore a hole right through the middle of the grout. And then we don't have problems with like flowing sands coming into our tunnel and flooding it. So this improves the ground through what we call compensation. So the term compensation means that we're compensating a weakness in the soil with something else. In this case, we're compensating it with grout in the void space, and we're turning the soil into soilcrete. So, this method can be effective for both fine-grained and coarse-grained soils. Again, that's my weakness. That should be an A. The problem with this, of course, though, is if you have a fine-grained soil, to allow that treatment to permeate into the void space can take a long time to complete, and so it can be very expensive. This method, therefore, is typically much more expensive than some of the other ground improvement methods that we've talked about, but it can be very effective for sure. Okay, let's talk about jet grouting. Jet grouting is another method that I've used before, and it works through reinforcement of the soil and replacement. It does not necessarily densify the soil at all. And by replacement, what I mean is that we're just essentially trying to push the soil out of the way or change the properties of the soil such that it's now basically a grout instead of a soil. So the idea with this is it's kind of like compaction grouting. It's a similar device, but our nozzle, instead of just being a straw that puts out gloopy balls of grout, it has a spray nozzle on the end of it, and it sprays under very high pressure, and it's going to spray grout into the ground, and it's just going to spin around and spray and this jetted grout into the ground and produce these soilcrete columns as the nozzle moves up and down into the soil. So, I mean, this can be effective in most soil types, fine-grained and coarse-grained. We can target specific depths. We can go in at angles. One of the fun things or cool things, we can drill through existing foundations and then go right beneath the foundations with it. Because we're not really pumping anything in or making big gloopy balls, we have an easier time with heave. But some downsides. This is one of the messiest methods I've ever seen. I mean, when it's spraying grout everywhere. Particularly if you're in shallow depths, because that high pressure can find its way to the surface. And again, quality assurance is difficult. We have no idea what kind of uniformity in our column we're getting. We just kind of hope for the best. Okay, another method that I've seen and used in my consulting has been a method called deep soil mixing. So with deep soil mixing, we are improving the ground through, interestingly enough, confinement. You could argue that it could be other methods too, like reinforcement and those things, but the interesting idea with deep soil mixing is that we're not really trying to get these super high strength columns here. What we're trying to do is we have this, like, think of it like a blender or something that we're lowering down into the soil, and it's turning. And as it's turning, it's pumping a grout mixture into the soil, and it's just mixing it all up to the point that we get a very nice, uniform column of soilcrete. And it's typically not very high strength. But these columns are usually placed adjacent to one another in a pattern to create like a solid wall or a lattice. And the whole idea is that we're trying to limit the amount of shear strain that can occur in the soil. So once the soil in the shear from the earthquake comes in and hits these columns, we're trying to limit the amount of shear that happens between these columns. That's why we call it confinement. So if we limit the amount of shear strain, then we limit the amount of pore pressure that's generated in between these columns, and thus we can prevent or at least delay the onset of liquefaction triggering. So this method can be very effective in most soil types. But the problem is these devices that it uses require a lot of space. They have a big boom on the crane, and so they require a lot of overhead space. Though, again, I wouldn't be surprised if these clever ground improvement contractors have come up with a low overhead device that could put in these soil mixing columns beneath structures. You know, one of the things, too, there's different methods I've seen with these mixers. For the levees, I've seen a device that puts down 3 adjacent augers, and so these augers are literally just right next to one another. So it just turns, and these augers go down the soil and back up and down and back up, and so they just churn and mix the soil as you pump grout into it, and that's how it gets its column. So that's going to produce a very long and deep but narrow improvement soil column. Another method that I think Malcolm Drilling was the first I've seen use it is called the cutter soil mixing, or CSM, I think is the short term for it. In this technique, there are 2 wheels, and sometimes you may even have a third wheel, but the ones I've seen have only had 2, and it basically has, you know, teeth like this. So it looks kind of like a scary, you know, torture device or something like that. But these wheels turn, and as it pushes down in the soil, it chops the soil up and sends the soil up into here, and they pump grout into here as well. And so everything just gets churned up and mixed by these cutter soil mixing blades. And you know, this device goes down and up and down and up, and you get a very uniform and reliable curtain of improved soil using this cutter soil mixing technique. Okay, another method that I haven't really seen used commonly, and probably because of permitting reasons, is deep blasting. So the idea is we're going to try to densify the ground at targeted layers by introducing pulse-like energy that's going to hopefully densify the ground, liquefy the ground. It blows water clean out of the ground when you do this. Because, I mean, we are purposefully trying to liquefy the soil in order to densify it. So think of it as pre-liquefying our site before the earthquake comes. And so this method can work really well if we have a loose, cohesionless soil. And the nice thing about it is explosives are super cheap. So this can be one of the most cost-efficient and effective ways. But it's not very good at shallow depths for obvious reasons. You know, this isn't a minefield. We're not trying to blow the ground up. It's just we're trying to densify the ground. And you can imagine that it's very noisy and definitely induces a lot of vibrations. But if you need to improve a large area that's comprised of a clean, loose, cohesionless soil that's saturated, and you want to do it in a cost-effective manner, blasting might be a good alternative. Another technique that is gaining more and more traction is the use of what we call earthquake drains. So Everyone in this class should be familiar with the idea of prefabricated vertical drains, or PVDs, or also known as wick drains. Earthquake drains have a similar concept, but earthquake drains are, if a wick drain looks, something like this and has some ribbing on it, an earthquake drain is basically like this, and it's completely open. It's just like a giant PVC pipe that's perforated, basically. And they put these pipes down into the ground. They don't really drill them. They actually just push them down into the ground with a mandrel, and then the mandrel comes back up again. So it's similar to a wick drain. So installing them can be very, very quickly. And the idea is that we're going to improve the ground, remediate against liquefaction by improving the drainage. So the idea is we're never going to let the pore pressures elevate to the point that we have zero effective stress. And it's been shown to work pretty well under relatively small seismic loads. And man, you can install these drains down to some pretty deep depths. I've heard of drains being installed down to 85 feet or so. The problem is that these drains remained untested in the field and in major earthquakes, and so we don't really know how well they're going to work. A lot of researchers, including Professor Rollins here at BYU, has done a lot of research with these earthquake drains on shake tables, and have shown that even under enormous shaking that they do reduce the amount of settlement and the onset of liquefaction. Here's the problem, though. With earthquake drains, your ground is still going to settle. You're not eliminating that, because you're still, what you're doing is you're increasing the water's ability to get out of the ground. So you're going to have some volumetric deformation, and you're going to see some settlement. The only catch is it's not as much settlement as you would get if the soil liquefied. So this ground is still going to settle. It's just not going to settle as much. So we still need a whole lot of research on this method, particularly in the field in a major earthquake. One of the obvious solutions would be, if you want to prevent liquefaction, is just get water out of the soil so that it won't liquefy. So we're going to improve the ground through drainage if we do dewatering. So dewatering means we're just going to put a big well in the ground, we're going to pump the water table down, and the water is going to go, and we're going to put it elsewhere. So this generally, when I've seen this, it's been for temporary applications. Rarely have I seen, a permanent dewatering solution with pumps. Usually, if it's a permanent solution, we're going to install some permanent drains. The drains are going to be just draining water out of the region and sending the water somewhere else. So we're not mechanically pumping water out, we're just allowing gravity to drain the water out of the site. There's problems, though, with dewatering. It can definitely have some environmental consequences. You can induce settlement all around the surrounding area when you draw the groundwater down. And there's usually a ton of authorizations and red tape that you have to go through if you want to do permanent dewatering at a site. Because if you're going to be pulling the water down, you've got to be putting the water somewhere. So where are you going to be putting it that won't be environmentally harmful and those kinds of things. So yeah, this could be a big one. Now, here's one that we did a lot in my consulting practice, and we just call it remove and replace. We're going to improve the ground through the replacement. We're going to dig out the loose, bad soil, and we're going to replace it with a non-problematic, compacted structural fill that's going to have a high relative density, so it's not going to be contractive when sheared, it's going to be dilative. I can tell you from experience that this method is always going to be the most economical solution to the problem as long as the problem is shallow. If you're within 20 feet of the ground surface and that's where your problematic soil is, I promise you that removal and replacement is going to be your most economic option. The downside to this is you're going to have a lot of mucky or loose soil that you're pulling out of the ground, and you've got to haul it away and put it somewhere. That can cause some problems. Now, if you're going to try to do removal and replacement at deeper depths, depths greater than 20 feet, now we can be talking about expensive solutions because you have to use specialized equipment. It can be a problem. One of the things that we have to make sure that is when we're replacing the soil that we're not just dumping new sand loosely down into the hole. Typically, when we excavate out these problematic soils, we're below the water table, and so if you just dump soil down there, oftentimes what happens is the sand just settles in the water, and it settles in a very loose manner, and you can actually make the problem worse. You have to put material down there that is self-compacting or that's very, very angular, and so slag is a great thing. Like that's a byproduct of mining. Very angular and coarse gravel that's going to get down, and when it tries to shear, it's going to lock itself up, and so you're not going to get liquefaction. That's the kind of stuff we're going to want to use when we replace our material, especially if we're below the groundwater table. So, all these methods of ground improvement are the main forms of ground improvement out there, but as I mentioned before, there's lots of tweaks and new things being introduced constantly by these clever and creative specialty contractors. So here's the truth. If you go into work as a geotechnical engineer, unless you go to work for a specialty contractor, you will probably never design the nitty-gritty details of a ground improvement. You're going to hire the contractor, and they are going to do the design, the implementation, and the QA/QC for the soil improvement. And basically, you're just going to be looking over their shoulder, making sure that they're doing a good job. So it's really important then that you be familiar with the concepts of ground improvement, and you understand the strengths and the weaknesses of the different approaches that we've discussed today, so that when you talk about options with ground improvement contractors, you can speak their language and you can raise your concerns. Now, a really cool tool that's been developed in the last, I would say, 4 or 5 years has been through a research project through the Strategic Highway Research Program, and it was being led by a Professor Filtz at Virginia Tech University. And what this was is a web-based tool for engineers, for the public, that will help them identify which alternatives of ground improvement could meet their project-specific needs. So it's a cool website. You go there. I wonder if no, that's not a link. Oh, maybe it is. Here we go. So you can see there's going to be a login. There's going to be a password. So you need to register. But once you go in and you register, it's going to give you some prompts, and you can select check boxes that relate to your site or don't relate to your site. And then at the end of the day, what it's going to do is it's going to help you. It's going to list some ground improvement techniques that might be feasible for your site and that you might want to look into. So this is a really useful resource for engineers, and I encourage you guys to create an account and to check it out. So that's the end of the lecture today. I hope you found it helpful. If you have any questions, please don't hesitate to let me know, and I'll look forward to seeing you guys in the next lecture.